All right, so this is my lecture on statistics, and what I want to use is there's actually very little in our OpenStax textbook for contemporary mathematics. So this is chapter 8, and notice it starts on page 815, statistics, but what I actually do, so I want to skip all of this here and go straight to page 912, which is the regression. And let's see, one page up, there it is. So here we go. In statistics textbooks here, what they start out with is, as they're talking about social sciences, they are pretty much looking at straight line regression curves. And what I want to introduce is, as you notice from the physics data, is other kinds of statistics, regression curves that we also came across in some of the other examples, the not physics examples that I provided. So this one here would be a parabolic one, yes, and my example is you could easily find that in free fall data in physics. So I'm going to scroll a little bit down here. We didn't come across this one here, this sine or cosine curve, which is also called a sinusoidal curve, regression curve. And as I said here, this could be a temperature data throughout the year, and there are similar things like that. Temperature data throughout a day, something like that, that gives you these kinds of curves. This one here is then obviously a linear regression. Looks pretty good. By the way, they actually don't tell us in some of these examples what it actually is. They just give us some made-up data here for us to look at this one. This one here would be a negative correlation, but it's still a straight line one, simply meaning that when one variable gets larger, then the other variable gets smaller, but it's still a correlation. We can definitely see that. So I'm going to scroll a little bit down, and here is this is a perfect or near perfect relationship regression. In this case, it goes down, and that would be kind of like natural sciences, physics data, because in other social sciences you just cannot have those kinds of perfect data because your variables cannot be measured that accurately as they can, as I keep saying over and over again in physics, where we are able to measure very, very accurately. So here we go, and then there's that typical one here, perfect data, physics engineering is my example. And I think that's all I had from this particular chapter in our contemporary mathematics book. So I'm going to go over to actually the introductory statistics textbook, also from OpenStax, so it's also available to you free online. Okay, I'm going to give myself a break here. All right, so let's go over there. I took my break here to review what I wanted to talk about. So, and again, this is from the other free OpenStax textbook on statistics. So here we go. A little introduction here. Usually what they do is linear regression. And we have used that formula in there, but of course I did use more than just linear for the physics as well as for the social science data that I introduced doing this particular unit right now. So anyway, scroll, I think it's on the next page here. Nope, a few pages down. So here, quite a bit of information in here too that apparently I am skipping here. So here we have a few examples. And we can see a correlation here, we can see one here, probably not here, right? Well, it says kind of weak, I would say. Really, really weak. We can see a correlation here, but there is this kind of outlier here, and that would have to be discussed. Is there a nice correlation here? And this is just a fluke data point that we should ignore, or that we perhaps should remeasure. So this could be still a fine, valid correlation here. Just review that outlier over there. All right, so here that kind of, looks like, as I say, exponential growth. As I put on the side here, bacteria, population, virus, infection, human population curve over the last century, so from the late 19th century until now, has been really exponential. It should be, I'm not sure about my lifetime, so into the 2050s, toward the end of this century, it should be leveling out, hitting a top plateau. So because Earth has only so many resources. The human population can no longer increase exponentially. Bacteria, well, again, or virus infections depends on how much resources they have actually to increase their population, but they also should plateau out. And of course, this one is just a joke here. Yeah, it's not a butterfly, and there is no pattern here. All right. Again, a few pages down. There's just, yes, I could do all of that, but by using Desmos, we kind of get around this, and I just present you the results and how to analyze the data and really kind of minimize the kind of math that's behind it. I still have you do math, as in the regression curves, and look at the various equations there that you get for the quadratic or the square root or the exponential or the straight line or the logistic, what have you. I mean, we have covered quite a bit. So this one here on the temperature versus ice cream cones, as that was one of the projects here. Notice they gave us good data. They made sense, right? But they didn't actually tell us, is there a source or study that's cited or some kind of vendor who actually kept track of that? Again, the data do make sense. But we also have to look at that, well, we would like to have a source for these data. Ignore this one here. I'm not talking about residuals. So let's see. I think the next one is actually quite a bit down. So I just came across this word, hypothesis testing. I'm not doing this in this particular unit here. That's story for a different day. I may or may not do it in this class or just leave it out. So let's see. Next page here. Here we go. So this one outlier and the next one outlier. I'm going to start with this one here. So here you see kind of a nice correlation, but there's definitely an outlier here. And that could either mean that if you trust this correlation here, that you say, oh yeah, this makes sense and the data are good. They're not perfect physics data here. You can see that too. So there's some kind of random error in here. But if you trust the data and you can say, okay, that one is an outlier and I should ignore it, especially for physics data. That one is just something must have gone wrong in the measurement. And now due to one of two things, or both, ignore that data point, and then even better, remeasure that particular data point. And in physics, for example, you would see that, oh, now that outlier is actually gone. I've remeasured it. I had a wrong measurement before, and actually my dot would actually move up here to be in line with the other data. So that would happen in physics. In the social sciences, well, you could perhaps remeasure that. And perhaps you should, yeah. I'm going to go back to the other one. This one here, yeah, there is an outlier. It's not as extreme as the other one. Notice the y-axis, the way it's labeled, final exam score in some kind of class, and here third exam score. And you would think that for different students, that there is a correlation. The better they do on their third exam, the better they're going to do on their final exam, right? And so this correlation makes sense, and yet there is an outlier. Well, I would say this is actually a valid outlier. Probably what happened is that this particular student scored quite low on the third exam and figured, I need to study a lot. And then he or she did very well on the final exam. And so this kind of outlier in that sense makes sense. Of course, the alternative is here, oh, I'm going to cheat on the final exam, but let's give them the benefit of the doubt. They've studied really hard, and that's why this outlier appears here. All right, so beware of outliers is what I'm saying is, but in this particular case, it can be relatively easy explained why it's there, and no, don't kick it out. In this case here, probably something went wrong when we measured this particular data point, and we should repeat it, which is better than just ignoring it. Ignoring, by the way, is a valid thing too if you cannot remeasure, but measuring it is usually better. I think that was actually, nope, there's one more. So this one here, consumer price index here over the decade since 1900 until about now. And we can see that the data nicely increase. And for this particular regression curve, I wouldn't really put an exponential in there because that would mean that the CPI is just going to skyrocket in the near future. And that's, unless you have inflation, is really not going to happen. I mean, extreme inflation. It really is not going to happen. It's probably going to plateau out as well. So what I would do instead is I would say, okay, throughout the most part of the 20th century, it's kind of like a straight line here, and then it's a straight line here starting around 1980 or in the 1970s. It's just that the slope is steeper, and at some point it's going to plateau out. So I would deal with the data in a different way. Again, I wouldn't put an exponential on this one. That's actually it in this particular chapter here from this statistics textbook, and then we will find our other examples in here, or some of them, and I'm going to actually do those next and look at the Desmos results that actually I got. And again, I'm going to take a break in order to review that for myself. All right, so let's look at the data, respectively. This is the way I came up with them here for the projects. So let's see, start out with the Olympic swimming here. Yeah, this is pretty stretched here. I have to click on that little plus here, and then I have this nice image here, and it's a little bit stretched. I really adjusted it nicely, but just for the full screen, not for me recording here. So it's a little bit stretched here of these three young women, the gold medalist here, Fanny Jurek and Mina Wiley, both of them of Australasia, which in 1908 and 1912 was the team between Australia and New Zealand that attended the Olympics. And the third one is Jenny Fletcher of Great Britain. And so when we look at the data here, and I'm not sure why the women's data are not, there's the correlation curve, the regression curve. So here are the women's data, and we can see that the Olympic swimming times are getting faster because they're getting throughout the century. Down here you see the 50-100, so this would be about this would be 1950, and this would be the year 2000. And then here we would have, I believe the year was the last one, like 2016 maybe. So the times are getting faster because they're getting more and more athletic. Here's an outlier, I guess. So on this year, 1952, they were just as fast as they were 16 years before. In 1936, by the way, there's World War II in between here, so this is the second Olympics after World War II. So yeah, there's a little bit of an outlier, and then we can see, well, but the times are getting faster. That makes sense because they're getting more and more athletic. The men, by the way, same thing. They're getting better and better throughout the century, and so on. And then it should level out. It should hit a lower plateau, and the B here, which is the would be kind of like the, if it was a straight line, would be the B-intercept, but here it is actually the asymptote, so the horizontal asymptote, and it says here 48 seconds here, and notice that this last time here is around 52, 53 seconds. So the women can definitely get as low as that. Notice that the men are already faster here in the 100-meter freestyle swimming. However, when you look at these data here for the men, they do follow kind of like this exponential decay curve. However, when you go over here, this goes way too low. This is like 31 seconds right here. You can see that. And no, that would be superhuman. That would be beyond human capacity of what they could do. So they're not going to get there. So these kind of graphs, they do describe the data relatively well, but you would have to question what's going to happen here in the future. That's probably not right. All right. I'm going to go to the next one. I'm going to close this folder here and turn this one off. I'm going to go to the age versus height data, and here we go. And there's the data. I do not have an image here. The last one that you saw was free from Wikipedia, so I have to abide by copyright rules. So you don't see one here. I couldn't find one for this one. Here the data makes sense. This is kind of like upside down exponential, or I call it the charging capacitor regression. This one here with the m times 1 minus the e to the something x, and then there's also a plus b in behind here, which is also again the plateau plus the actual coefficient in the front here. So we can see that these data kind of make sense throughout adolescence, and even the, I think it's the red curve is the one for girls, and the orange one is the one for boys. And we can see that the boys, when they get out of adolescence, are on average taller than girls. And then we know this one here as well, where the girls actually are for a while taller than the boys in late elementary school. Again, they're pretty good here, these kind of data. Also, when you go to age 0 here, yeah, that kind of makes sense, in the neighborhood of 25 inches when they're born. But don't go beyond that, because you get really unrealistic results here. Notice that the girls plateau out around, 75 inches. That's like 6 feet and 3 inches on average for the girls, right? And the boys are somewhere around 100 inches. That would be like 8 feet on average. So when you go beyond that, yeah, don't use those kind of regression curves. Within here, they're actually pretty good. All right. Before I turn on the ice cream, cones, and coffee, I'm going to make a little break here. All right, I'm back, so I'm going to turn this one on. There we go. I'm going to go here and there. I'm going to zoom out so we can see both of them. And what I had to do was, I couldn't find a good coffee and cream image here. I found one from Seattle's Best, but I just couldn't put it in here, because of copyright. So anyway, so here we see the ice cream data that are unsourced in the textbook. So they do make sense, but again, we don't have a source for it. And of course, this could be reproduced if we actually follow an ice cream vendor throughout the summer and see what happens with the sales depending on the temperature. Could be. And these are the coffee data, coffee consumption versus heart disease. And it's a little bit surprising that actually with moderate, but I did find a study that says that with moderate coffee consumption, heart disease actually goes down. So, all right. So let's see, I'm going to turn this one off. Here are the flu and COVID data. For the flu data, which is the one on the right here, I advise not to do a regression curve. Notice I put one there, so I'm going to take it off. So something must have, this one here is the 80s and 90s, and then something must have happened here around 1995, where all of a sudden these flu death data go quite a bit down. I believe this is what here, 20,000, 40,000, that kind of thing. So, and because something happened here in society, you shouldn't put a regression curve on here. You could put one here, a straight line here, and a straight line there. All right, the COVID data. So there we go. Again, I didn't put an image here. That's okay. So here are the ones for Italy. This is early in the pandemic. So this is, I believe, like 5 days after February 15th, 2020. So this would be here kind of like the end of February, and then this one here would be kind of into mid-March. So here we have Italy. It goes exponentially up, and it looks pretty good. And here we have South Korea. It also actually exponentially goes up, and then it flattens out. And you can find reasons for that, why Italy is still going exponentially up, and why actually South Korea is hitting a plateau early on because of what they did in society in early March of 2020. You can read about that, how that happened. And by the way, eventually South Korea did go up, if you take more data in here, and Italy also topped out at some point here. But I just took these two curves early on to show you that this one is definitely an exponential one, and this one here is what is called a logistic one. So where it starts out exponentially, so a population, for example, increases, you put fish in a pond and they increase exponentially in population, but then again, at some point the pond is a limited area, a maximum area, so at some point the population can no longer grow, there's no more space, so therefore it will level out here. So that's what a logistic curve is. So let's see, I'm gonna turn this one off, there we go. I think I have one more. I don't know if I have centripetal force in here. Maybe I do. Let's see. Oh, I do. All right. So there's centripetal force, and I think this is where you have the number of rotations, which is also the number of rotations, which is also the same as or similar to the velocity with which it goes around, the speed with which it goes around, versus the length of the string on which you have that. So you have this kind of like it says then here, a square root relationship from the length, which means it's actually a square relationship from the velocity. The variables are turned around. And I put it in here, again, a physics example that is nearly perfect. Notice that it's not exactly perfect, and that is because in this applet that I had you use, you actually, or I in this case, actually had to make real measurements, and they were not perfect accurately, okay? So therefore, like you see a couple or three that are slightly off. The, here we go. The regression coefficient still is really good, right? 0.996. All right. Again, put a physics example here just as a reminder that, yeah, in physics the data can be perfect or near perfect. Well, in the social sciences, excuse me, they don't, probably are not usually. Okay, so here's the United States, the rank when they joined or were admitted to the Union versus when they versus the area. I had to think about this here because, again, doing this one here distorted this quite a bit. The way I do this here, by the way, is I hold the shift key down and then I use my mouse to do this one here. So here's a map of the United States. There is this line here, and of course this line is heavily influenced by the large states here. Like this here would be Texas. What is this? The 41st state. What is the third largest one? After Alaska, by the way, is off the chart. You know, it's 660 up. This down here is Hawaii. So at first I was thinking, well, there can't be a correlation. Why should there be? Well, it turns out actually there kind of is. If you look closely at this one here, that the first 25 states, so which goes to here, notice they're all smaller than 60,000 square miles, and that's because they're all from over here, the original United States from 1776, and then the Constitution was written in 1789, and that's when it really came into existence. Well, the others here, the next 25, so all of these here, are from the westward expansion. So here you have the Louisiana Purchase, the treaty with Mexico over Texas. Here, this is the Guadalupe Hidalgo Treaty, 1848. This one is yours, 1846, so that after the Mexican-American War gave California and these other states here, which became other states, first territories, to the United States. And this one here is the Oregon Treaty from, boy, when was that? 1830s? I think 1813, somewhere around there, after the, is it the English-American War from the 1810s, that then ceded here the Oregon Territory to the United States, and then there was a border then made into Canada. So that's where all these here come from, and you can see that the area is much, much larger. Again, we have Alaska squeezed right next to Mexico, much, much larger here. It's kind of like an outlier here. So is Hawaii, so is, I think this is West Virginia, and this is Iowa. So of these 25 states, actually 20 that joined later, that joined last, 22 are actually larger than the 60,000 square miles, and that can be easily seen when you look at a map like that and the way that the United States did these treaties and admitted then these territories as states. All right, so interpreting data, regression lines, that was what I wanted to get across in this unit and in the previous unit, with some perfect data, such as from physics, and then, as I keep saying, from the social sciences, where the data are not so perfect, but you can still get a correlation. And I chose some where you can get one. You can also get some that you would have to question a correlation, or you don't get any at all. So I kind of gave you a smorgasbord of these kinds of data and regression curves. And that should be it.